Hi, welcome back to physics. We're studying waves right now, which, as you know, are disturbances caused by particles in a medium vibrating to transfer energy from place to place. We've recently learned about one way that waves are different from material objects, in that they can bend around corners or barriers to fill space behind them. This is called diffraction. We're going to use a couple of case studies now to delve deeper into the properties of waves, looking at two famous kinds of waves, the first of which is sound. Sound is a mechanical wave, and if you remember from the beginning of this chapter, what that means is it requires a physical medium to be moving. You can hear my voice right now because of the air in the room that you're in vibrating back and forth to carry sound waves through it. So most of the time, what we hear is sound waves propagating through air. That's not the only way it works, though. Sound also travels just fine through liquids and solids. You know this if you've been in a pool, or, say, knocked on a door. You may remember from the beginning of the chapter that sound is a longitudinal wave. What does that mean? Describing waves as longitudinal or transverse is just referring to the way that the particles of the medium move while the wave is being transmitted. In the case of sound waves, the fact that they're longitudinal tells you that those particles of air are moving in the same direction that the waves are. In other words, moving back and forth between your speaker and your ears, moving first towards one, then back towards the other, bouncing back and forth and back and forth. Now, that's really hard to picture, to visualize, or to interpret, so we often will diagram them as a sine wave, as you can see here, and you can think of that as transferring the compression zones where there's wave fronts or lots of air molecules kind of clustered together, interspersed with these spaces between where there's less air molecules, the density is lower, and that's the bottom of the sine wave or the trough. Now, one of the most important properties for analyzing sound waves is how fast are they moving? The speed of sound depends a lot on what it's moving in. Water transmits sound waves much more quickly than air, but even within air itself, the speed of sound varies quite a bit. The temperature can change it, the humidity can change it, lots of things will make that speed go up or down, which is tricky, although there is a nice average value that we'll typically be using, especially in this class, which is the speed of sound at STP. That's a chemistry principle that you may remember, standard temperature and pressure. The speed of sound at STP is going to be 331 meters per second, and that is, of course, on your handy-dandy reference table if you ever need it again. Hint, you will. So I'm first going to put up a couple questions. Here they are. I suggest you pause it for a moment and give these a try. I will link a video here with the worked out solutions so you can check your work later. Try those now. All right, just a couple more concepts to look at today about sound. The first is called pitch. The pitch of sound is whether it's, a high note or a low note, and the pitch is nothing more than your ears interpreting the frequency of that wave. So the higher the pitch of the sound, say like a whistle or the keys all the way to the right on a piano, those have a very high frequency. Your ear is receiving lots and lots and lots of tiny little waves each second, and it interprets that as a high note. If you're hearing low notes, like a bass drum or a tuba, you're hearing low frequency waves. You didn't know you could measure the frequency of a wave with just your ear, did you? Now you know. Last thing for today, which comes up often looking at sounds, is something called an echo. The concept of an echo is simple. Produce a sound and wait. If that sound wave moves away from you, hits some barrier, bounces off of it, and returns back to you, well, you can hear your own sound back again. The only tricky piece with that is remembering that the distance that the wave has moved is twice the distance to the object. Knowing this, you can use sound waves, which have a very predictable velocity, to measure the distance to something with very high accuracy. This is how radar and sonar work. So here's our last sample problem to try for today. If you shout down into a well and hear the echo of your voice 0.15 seconds later, how deep must that well be? Again, the worked out solution will be posted shortly. I suggest you give this a try. Thanks for learning physics with me today. I'll catch you next time.